Hello and welcome to Skeptics in the Pub Online. This is a series of online talks made in collaboration with most of the skeptics groups around the country and beyond who've been unable to meet in person since the pandemic, and a couple who are now meeting again in real life. So check out the list in the break if you want to see if there's a group near you. Just like the real events, this is a real event, of course, just like the real life events, we're going to have a talk about 45 minutes to an hour, and then a break, and then the Q&A. The difference is that obviously you can't ask a question in person here. So if you want to ask a question, head over to Slido. There's a link for that on the screen somewhere, and it's going to be in the Twitch chat as well. The Twitch chat is also a good place to hang out if your question is more of a comment. Our mods are going to be in the chat with you to help with queries, links. If you want to enable closed captions, they're going to help with that. And they'll be dropping in links if you want to throw us some money to help us keep going, if you want to buy some of our merch, or if you want to buy our speaker's book. Our speaker tonight is a mathematician, an author, a former Christmas lecturer, a TV presenter, and the Simonyi Professor for the Public Understanding of Science. He's going to be telling us about thinking better, the art of the shortcut. So let's have some clap emojis in the chat for Marcus de Sautoy.
Thank you. Well, it's so nice to be joining the skeptics in the pub, but unfortunately not down the pub this time. So I hope you're all sitting comfortably. Tonight, I'm going to offer you a choice. You can either take the long road. It's going to take you ages to get to your destination. It's rather boring, rather repetitive. Not terribly interesting views on the way, although actually, there may be a few dangers involved. You may have to avoid some kind of wild beasts, some things which might make you lose your way. But I've got a second choice for you, and that is that there's a shortcut. And this path is going to be slightly more tricky to negotiate, maybe. You're going to have to keep your wits about you, but it's going to get you to your destination more efficiently, more successfully, hopefully. And I think there'll be some interesting views on the way, that this is the path that I'm going to encourage you to take. And it's really the subject of this new book that I'm going to talk about, that Thinking Better, the Art of the Shortcut. And as was mentioned, I'm a mathematician, and I really have understood that it's my subject. Mathematics, I believe, is the art of the shortcut. People might know Daniel Kahneman's book, Thinking Slow and Fast, Fast and Slow. Our intuitive thinking is fast and generally very faulty. And he says we have to think slowly in order to be able to get to our destination successfully. But what I want to explain to you is that, well, you can think analytically and still think fast and get to your destination, but you've got to use these shortcuts that mathematics has come up with. I first discovered my own kind of shortcut that set me off on my own journey to dedicate myself to the art of the shortcut when I was at school, when I was about 12 or 13. My comprehensive school, my maths teacher told us this wonderful story about the young Carl Friedrich Gauss. This is actually a picture of him in his 20s, I think. But this was actually a story of Gauss when he was 9 or 10 in his class. And any mathematicians out there will know the story that I'm about to tell. And this is the story my teacher told our class, which really kind of made me think, oh, mathematics is a subject I want to dedicate myself to. It's the story about a teacher as well in Gauss's maths class who asked the class to add up the numbers from 1 to 100. And I think the teacher thought, wow, this is going to take them a long time. The long path is adding 1 plus 2 plus 3 plus 4. It's going to take the class a long time to get all the way to 100. Probably make lots of mistakes on the way. And I think that he thought he would be able to get a little bit of a sleep, a rest, because the class just take ages to do this. But before he'd even finished asking the question, the young Gauss had written down a number on his chalkboard and slammed it down in front of the teacher on his desk. I think the teacher thought he was being impudent, but when he looked at the slate, there was the correct answer, 5,050. And the teacher was amazed, asked Gauss, how on earth did you come up with that number so quickly? Add up all of those numbers, 100 numbers. Gauss said, Well, there's a shortcut to doing this problem. I can see all my fellow students are going from the beginning of the journey, plodding through the numbers one by one, adding them together. But what I did was to combine the beginning and the end of the journey. So to start at the beginning, but also at the end, because 1 plus 100 is 101. If you move a little bit further in from each side, 2 plus 99 is also 101. 3 plus 98, 101. So what the young Gauss had recognized is that there are 50 pairs of numbers all adding up to 101. So the answer very quickly is 50 times 101, 5,050. Now, what I love about this shortcut is that even if the teacher had said, okay, well, I'm going to set you an even more difficult problem. What about 1 to 1,000,000? Once you've dug that tunnel and realize the smart way, the better way to look at this problem, that shortcut gets you to the solution, however large you make the sum. And for me, this was just stunning to see this clever way to look at the problem. I remember my teacher saying, well, that's what mathematics is about. It's the art of the shortcut. And what I'm going to do over the years will teach you at school and if you go on to university is to learn these extraordinary different range of shortcuts that mathematicians have discovered over 2,000 years of considering these kind of problems where there's a kind of boring, slow way which is going to take you forever. But if you look at the problem in the right way, and what I'm going to show you over the presentation is kind of different ways of looking at problems that we've come up with, which give you a shortcut, then you can get to your goal as quickly as possible. Now, it's interesting. I think I found the idea of these shortcuts as a school kid really appealing because I was really lazy. I actually wanted to avoid doing any work. And I like the idea, you think cleverly, then you don't have to do any work. But actually, in my adult life, I actually enjoy my work. And, I enjoy being a mathematician sitting here at my desk thinking about problems. But what I don't want to spend my time doing is kind of boring, tedious work that is kind of feels like I'm not really thinking. I want to get to the things I really enjoy doing. So this is a really important point to make right from the outset. These shortcuts are not just about avoiding doing any work, which is kind of why I chose it as a lazy teenager. But it's more about getting you to your goals such you can dedicate your time to the things you do want to spend your time doing. So I rather like this division that Aristotle came up with between the two different sorts of work. He said, well, there's praxis. That's work for its own sake. That's the work that we enjoy doing. We don't mind spending time doing that work because it's the stuff we love doing. It's the proesis, the work just for an outcome, for the goal, the work that's just trying to get you to that end destination. And very often that's the work that we sort of, we kind of resent doing because it's just taking loads of time and effort. So my shortcuts that I'm going to try and present to you are trying to avoid the proesis work and get you to the destination so you can enjoy praxis, the work that you love doing. And then actually, this was Karl Marx's ultimate goal in his ideas about communism. I mean, communism was not meant to be simply about, the worker not doing any work. No, it was in a higher phase of communist society, Karl Marx wrote, labor has become not only a means of life, but life's prime want. So I'm going to give you a tour of some of the shortcuts that mathematics has come up with after the last 2,000 years and that I present in this new book, Thinking Better, the Art of the Shortcut. So we're going to start actually with some shortcuts that actually reveal that nature really enjoys finding fast and efficient and low energy solutions to problems, that in fact, just like me as a lady teenager, that nature itself is quite lazy and likes shortcuts. And so some of these shortcuts nature has found, and we had to kind of find as mathematicians, well, how do we produce a tool that will help us find the shortcuts that nature seems to find so easily? And this actually is the motivation for inventing what I think is one of the greatest shortcuts of the last 2,000 years, which is the idea of calculus, the differential shortcut, that this is going to be a tool which is going to help us to understand how nature finds things so easily. So nature has loads of lovely examples of using mathematics as shortcuts to low energy solutions. Take, for example, the honeybee. Why does the honeybee make its hive into hexagons? Well, the wax that it uses to make the honeycomb is actually very expensive for the honeybee. It costs a lot of energy. So it wants to try and find shapes that actually use as little wax as possible. So what's the shortcut shape that allows it to make its hive but without using too much wax? It could have been squares, for example, or triangles, or some other strange combination of shapes. Turns out that the hexagon is the shape that, when you put them together, uses the least amount of wax in order to contain that particular volume of honey. So nature has found for the honeybee this low efficient solution to be able to make its hive with as little wax as possible. And it's rather similar to bubbles as well. If you blow a bubble, it starts off as some strange sort of shape, but then settles down to this beautiful sphere. And again, the sphere is the shape that the soap film makes, which uses the least amount of energy to contain that volume of air that you put into the bubble. The surface area is proportional to the energy, and this is the lowest surface area. So nature seems to always want, if you put a ball on the top of a hill, it rolls down and finds the lowest place in the valley as the low energy solution. And often this is what is happening with bubbles. And so if you take a particular sort of frame and put a soap film over it, the soap film will tend towards the shape which uses the least amount of energy to cover that frame with soap film. And we humans have already exploited the fact that sometimes you can just use nature directly to find the low energy solution, the shortcut solution. So, for example, if you go to Munich, to the Munich Olympic Stadium that Fry Otto built, it's this beautiful sort of canopy, very organic kind of shape. And actually, he built this stadium by modeling it on a particular frame and then covering the frame in soap film, and then he just scaled that up, and he knew that the soap film was helping him to find shapes for the stadium which would have low tensile energy, so it would be the most sort of effective way to cover that canopy without too much tension on the whole building. So we've tapped into kind of the idea that nature knows how to do things quite well. And actually, it's even a kind of philosophy in science, Maupertuis kind of capture this idea that in everything, nature is thrifty. So nature is a bit like that lazy teenager that I was as a kid, likes to find these efficient low energy solutions. So it's quite good at finding these shortcuts. Another interesting example is light. So light does this thing where, if you're in a swimming pool, you seem to be shorter in your legs. There's kind of this weird bending effect that if you put a ruler inside a swimming pool, then the light, as it comes out of the water and into the air and into your eye, seems to take a slightly strange route, which causes this kind of bending of the ruler or the shortening of your legs. And this is because, again, light is always after the shortcut, the shortest way, the fastest way to get to its destination. So because light travels slower in water than it does in air, it needs to get out of the water as quickly as possible to take advantage of the higher speed in the air. And so it finds this optimal point in which to exit. And this is kind of curious, how does it know which path to take? I mean, what is the kind of shortcut it's using? Well, it appears that probably it's tapping into the idea of quantum physics, that actually the light is going into sort of superposition, trying all the different paths, and then collapses into the path which is that fastest route from the source to the destination. But how would we do it? We can't try all the different possibilities. That's very inefficient. You can tap into quantum physics as a photon. But for example, here's this little challenge. So here's the lifeguard running across the sand. It can run across the sand faster than it can swim to the drowning swimmer. So what's the optimal point at which to enter the sea in order to be able to get to the drowning swimmer as quickly as possible? So you might say, well, maybe I should spend as little time in the sea as possible and sort of have a perpendicular line towards the swimmer from the shoreline. But that means spending more time on the sand, and that actually isn't optimal. So there is a sweet spot. Again, you could model this using light going through two medium with the same speeds in each sand and sea. But what we actually do is to use this fantastic tool that Newton and Leibniz and his their contemporaries came up with. The calculus says, okay, well, let's consider the distance from along the shoreline, call that x, and what we want to do is to find the value of x, the distance to enter from sand to sea, which will minimize the amount of time spent getting from the lifeguard's beginning point to the swimmer in the sea. And the calculus is wonderful at finding these minimal or maximal solutions to things, and it's that we'll use in order to find that sweet spot. What is the x which will get us to my destination as quickly as possible? So we've come up with this tool which, given a whole dynamic range of possibilities, it pulls out the kind of solutions which are the shortcut to either getting to a destination quickly or maximizing your profits in the economy or whatever it is that you're modeling. It was a great tool to understand a kind of world in flux. And one of the interesting uses that it got put to in Newton and Leibniz's time was a challenge that had been out there for some time, which was, again, about getting the quickest from one place to another. But this wasn't trying to rescue somebody at sea. This was trying to construct a roller coaster ride, basically. What is the curve that will get you from the top of the roller coaster to the station at the bottom in the fastest way possible? Is it maybe a straight line that will get you there? Or no, maybe you need to do a bit of a curve, so perhaps a quadratic between the top of the roller coaster and the station at the bottom. And so calculus was taken and said, okay, let's look at all the different curves that are possible to get from A to B. And then what is wonderful is the calculus hones in and finds you the fastest path. It's the shortcut to finding the shortcut. And it turned out to be a very curious curve, actually, because it turns out that the curve you need is the one mapped out by a bicycle wheel. If you put a pen on a bicycle wheel and you started the bicycle wheel, you can see it on the left, for example, and you start rolling the bicycle wheel along and you see what the curve is that's mapped out by the pen on the edge of the bicycle wheel, you get this particular type of curve. And it turns out that you need to turn this curve upside down, and this is the curve which will get you from A to B as quickly as possible. And what often happens is that actually you have to go below the height of the station and come back up again, that you're using the fact that gravity will pick up the speed as you go down. And of course, it will be slowing as you come into the station, but that actually is the fastest path. Anyone who's been to a science kind of center might have seen this curve. Actually, it's one of the nice experiments people do where they've got three curves, quadratic, a straight line, and this slightly unusual curve, which seems to have to go further to get to its destination. And then you set off three balls at the top, and you see that this upside down curve is the one that gets you there quickest. But it took this tool of the calculus to find that this is the curve which gets you there best. So I think the calculus is a great shortcut for finding these efficient solutions. And it sort of does what nature would do, kind of using its kind of skill set, but we can't do what nature does, but we can use the calculus instead. It's interesting because, that's a shortcut it's going to take you a little bit of time to learn. Maybe that's not a shortcut. If you're not a mathematician, you wouldn't call that a shortcut. But I would say that one of the things here is that what I hope to tell people is that what are the shortcuts out there that, maybe you don't know how to use this shortcut, but you know somebody who can help you with it. This is a tool which will find you these efficient solutions for you. So I do like the calculus. It is one of my favorite shortcuts. Of course, in this modern world, we're inundated with a huge amounts of data. And one of the challenges is trying to find some way to understand in this huge amount of numbers what's going on in the data. So we've really needed some sort of shortcuts to be able to understand what are the messages inside here. Do I have to look at every single piece of data really to understand what's going on? And again, mathematics has come up with some great shortcuts to be able to understand the message inside data without having to look at everything. One of my favorites, I understand that the skeptics in the pub are big cat lovers. And I do have a cat, but she's very temperamental. And even though I try to bribe her tonight to take part in my talk, she's gone out mousing. But at least I've got a cat story for you, because when I was a kid, and some of you may remember this advert, there was a wonderful advert for cat food for Whiskers, which claimed very boldly that 8 out of 10 cats preferred Whiskers to any other cat food. And, we had a cat as a kid, and I was always rather perplexed by this because I don't remember anybody coming round and asking our cat what sort of cat food it liked. And I sort of wondered, how can they make such a claim? They haven't asked my cat. How can they know? And it wasn't until university that I sort of learned about the, how many cats would you need to ask in order to be able to make such a bold claim as this? 8 out of 10 cats prefer Whiskers. Now, there are 7 million cats in the UK. So how many cats would you have to ask to be able to make such a bold claim? So, for example, how many cats would you need to ask? We're talking about sort of a sample set to be able to be 19 out of 20 times that sample will be 5% away from the true value in the whole population of cats. This is kind of the gold standard for a sample. You want to get to that level of 19 out of 20 times, you're 5% away from the true value. Well, in 7 million cats, it's an amazing shortcut. You can just consider basically 250 cats and doing a survey of that small number will give you a great insight into that large data set. And I think that's really, I was surprised by that when I first learnt it, but it's an incredibly important shortcut to know about, because you don't want to waste your time spending lots of money going and asking, hundreds of thousands of cats, when actually 250 will get you away with knowing actually a lot about those cats. And of course, one of the important things is you've got to make sure that sampling is random, and that's somehow one of the issues about making sure you don't bias your cats by only asking cats that live in Kensington or something. But the ability of mathematics to know how much data to look at before you can make a decision is one of the really powerful properties of maths. And one of the ones I really like, it's helps you actually to play a game. It's actually a game show, Deal or No Deal, but it's a game that I think actually comes up in quite often in life. How much data do you need to see in order to make a decision when you're faced with some decision to come to in life? Now, Deal or No Deal, of course, actually, the different sums of money that are in the boxes. What you don't know is which boxes they're in. But there's a slightly more tricky version of Deal or No Deal, where you say, okay, well, I suppose I've got like 26 boxes, but I don't even know what the prize money inside those boxes are. So it's not like I know one has $1 and one has $1 million. I actually don't know anything about the value of the prizes inside there. So I've got to get a feel. Is this a game show that has the possibility of millions, or is it just, are we competing for pennies? So how much of the data set, how many boxes do I need to open to start to get a feel for what's out there? And I think this is a kind of dilemma we face quite often in life. If you're looking to buy a new flat, for example, and you go out and you look at one flat and it looks really fantastic, but you wonder, well, maybe there are even better flats out there. I've only got one flat. I've got nothing to compare it with. So you need to get some data to start making a comparison. I think the classic one is your boyfriend or your girlfriend. You go out with somebody at school and they seem terrific, but, should I marry them? You just not sure that there might be even better people. It's the perfect one out there, and I need to spend some time surveying the territory. So how many girlfriends or boyfriends you need to go out with before you should sort of take the plunge? Well, mathematics can help you. Top of the pops of numbers in mathematics, obviously pi probably hits the number one spot, but the number two spot is probably held by E. This number 2.71828 goes off to infinity, like pi never repeating itself. This is a very important number, and it's important for this particular problem of how much data to look at, because it turns out when you analyze this problem that what you discover is that to try and optimize getting the best girlfriend, boyfriend, flat, or the best prize in those boxes, what you need to do is look at 1 over E of the proportion of all the data that's there. So 1 over E is about 37%. So you need to look at 37% of the data. And then here's the strategy. So that gives you a sort of sample, 37% of what's possible there. So in the game of deal or no deal with where you don't know the values, you look at 37% of the boxes. That gives you a good kind of feel for the numbers. And then what you need to do is to choose the box which beats all the boxes you've had up to that point. Because obviously in all of these games, the whole point is that you can't go back and choose something that you've seen already. Once you've given it up and looked at another one, you can't go back. Once you've dumped your girlfriend or boyfriend, you can't go back. Once you've opened a box, you can't go back. So you need to look at 37% of the data and then choose the thing which beats everything that you've seen up to that point. Now, this clearly isn't a guaranteed strategy to get you the best thing, because the best thing, 1 out of 3 times, the best thing has already occurred in the first 37% of the data. But actually, this strategy, 1 out of 3 times, actually is the most optimal strategy for getting the best that there is in that data set. And that's the best you can do with this. If you look at fewer or more boxes, then you're decreasing your chances of getting the optimal solution inside there. So I think it's amazing use of this number 2 in the bestseller list of mathematical numbers to help you to know how much data to look at before you take the plunge and choose what's next. 1 out of 3 times, that will get you the perfect partner. So the data shortcut, really important in this modern age to know how to navigate all of that data. One of the most powerful shortcuts I found doing mathematics and actually more generally is the idea of finding a good picture for a problem that you're interested in. I think, it's interesting when you say a shortcut, often it has a rather pejorative sound to it. It sounds as if you're cutting corners. And so I need to make this very clear. No, I don't want a sort of shoddy way to build a house. I want a shortcut which is going to build my house and it'll stand even if I had taken the long way. So, but I think these shortcuts, the diagram shortcuts, do have a bit of a quality of saying, okay, I'm going to throw away some information, but a good diagram is saying, okay, I don't need to know this information. You're crystallizing what you do need to know. And that's what the diagram can often help you to do. And these diagrams are very powerful. One of the first uses of diagrams to kind of capture data changed policy in the British government. This is the very famous diagram of Florence Nightingale, the so-called Rose diagram, which she used actually to persuade governments that they needed to do something about sanitation in hospitals. She'd gone out to help out in the Crimean War in 1854. And she was horrified to see that most deaths during that war were not on the battlefield or from injuries. They were actually due to disease. And this was illustrated perfectly when the sanitation committee came out, cleaned the hospitals, and suddenly the number of deaths plummeted. And so Florence Nightingale realized that something had to be done about the sanitation inside hospitals. And she tried to persuade the government when she came back. But it was eventually a diagram that she created, which persuaded government to do something. And it's this diagram here where the blue petals in this rose diagram, the area corresponds to the deaths through things other than injuries from warfare. These are the deaths due to bad sanitary conditions in the hospitals. And when the sanitation committee came and cleaned things out, suddenly these blue petals dropped in area. So the first year of the Crimean War is the rose petals on the right as you're looking at it. And then once the sanitation committee came in, suddenly you see that drop from January, February, March, April of 1855. And this helped to persuade government to change its policy. And of course, actually, we've experienced this during the pandemic, that the data is often quite hard for people to interpret just as a set of numbers, but you put it into graphs and the right sort of graph, you can really help people to understand the impact of, for example, vaccination or masks or whatever. But you have to be careful. A diagram, the whole point is sort of throwing away information, but how much do you need to throw away? Sometimes people want to put too much data in. They're rather precious about the information. And so, if you think a map is a great example of a diagram which you kind of distill the kind of lay of the land into a smaller piece of paper. But I rather like this story that comes from Lewis Carroll of a land that couldn't give up on all the details of the country. And so their diagram of their country, they're very proud of. So we actually made a map of the country on the scale of a mile to the mile, so they could get every single detail in there. Have you used it much? Says the narrator. Well, it's never been spread out yet. The farmers objected. They said it would cover the whole country and shut out the sunlight. So we now use the country itself as its own map. And I assure you it does nearly as well. So, of course, defeats the whole object of a diagram or a map. Borges, actually, the Argentinian short story writer, also has this idea of a country that's its map is as big as the country itself, which isn't much use. So our best diagrams, of course, are maps of maybe the universe or the solar system. They're very small, which sort of capture the essence of what you're trying to communicate, but aren't literal pictures. So, for example, you've got Copernicus's wonderful sun-centered solar system. He wrote, a long book, 200 pages, trying to explain his theory. But the thing which really persuaded people was this little picture early on in the book. And of course, this isn't a literal picture of the solar system because we have ellipses, not circles. They aren't evenly spaced out. But he threw away all of that information because what was important was just he wanted to communicate that it's the sun in the center and the planets going around. Any chemists out there, of course, your blackboards are covered in letters and lines which capture molecular structure in a beautiful diagram. And particle physicists, these Feynman diagrams are amazingly powerful shortcuts to understanding very, very complex mathematical path integrals. At the time, they were trying to understand what quantum physics was sort of trying to tell them, and Feynman really couldn't understand it, and he had to come up with this different way of looking at the problem. And it's now become, the go-to shortcut for anybody trying to understand particle interactions is you draw these little diagrams. So these are great examples of throwing away stuff that is confusing you, but still having enough there to be able to say something meaningful. Another interesting example is the diagram of DNA when Crick and Watson wrote their Nature paper and they wanted to communicate their discovery of this double helix. Their initial diagrams, which I've seen actually in the Wellcome library, they're very confusing because they can't resist putting the extra structures and molecular formulas that they've kind of discovered on site, and you lose kind of sight of what's going on. And Crick took this picture that they made back to his wife, Odile Crick, who was an artist. She did portraiture. And Odile kind of saw what the essence of their idea was. And she drew this beautiful double helix and threw away a lot of the information. But it captures absolutely the message they wanted to communicate. And it's that diagram that's the one that's in the Nature paper done by Odile Crick. So diagram is very powerful, but sometimes you can throw away too much information, keep too much information. Sometimes you can mask the data in dangerous ways. So we know that diagrams can be used maliciously, especially sort of by journalists, either knowingly or unknowingly. Here are a few examples of things to watch out for. So the diagram on the left, this was a graphic used by Fox News. Well, the one on the left was the one that was used by Fox News, and they were trying to illustrate the impact of removing Bush's tax cuts would have on taxes for individuals. And so they wanted to illustrate, wow, your taxes are going to go up massively if this thing is dropped. And so you see what the taxes are now, 35%. In January, it'll go up to 39.6%. And it looks a massive difference. But what Fox News sneakily did was to start the graph at 34%. So if you actually, okay, that you could do that, but most people didn't spot that. If you set it at 0, well, actually, it isn't that big a difference. And so it doesn't have that big political impact that they wanted to imply that this tax cut was going to have. So so that's important to kind of know where you're measuring from. Another cunning one, this is profits that a company is trying to persuade its investors that its profits are fantastically better than its competitors. So, company A has 1 million profits, company B, 2 million profits, but look at company C, massive, great purple profits there, 5 million. But you can see the clever thing they've done, because you actually need 25 copies of company A's profits to cover that purple block. So the height is certainly keeping track of the profits, but they've also enlarged the width. So this is a very common trick to make it look like your profits are so much better than the other companies. There's something intriguing, actually. We go back to that Florence Nightingale diagram, because she actually used area to measure the deaths in patients. And if she'd actually used just height, if she'd done a bar graph, the effect would have even been greater to see. So she actually minimized her impact by using the kind of spread of the rose petals as well as the distance from the center. So in a way, she made a mistake in using that particular model to show the data. So certainly diagrams are a fantastic, powerful shortcuts, but need to be used carefully. In fact, a diagram was used as a shortcut to help in my next kind of suite of shortcuts, which is, I said that we live in a very data-rich age, and finding shortcuts to navigating data is really important. I think the other quality of our modern age is that we live in a very networked society, both our social networks, networks of travel, internet, of course, and network, trying to find your way around the internet. And so we've had to come up with clever, efficient ways to navigate the networks that kind of run our lives. And one of the beautiful shortcuts that was used to understand a kind of network problem actually involved a diagram. And again, it's another of those kind of classic fairy tales that we tell our students, like that Gauss story of the numbers from 1 to 100. This is a story about Leonhard Euler, one of the other great shortcutters of mathematical history. And it's about the story of a town, Königsberg, which in the 18th century residents of Königsberg face this challenge that there's two branches of the River Pregel come into Königsberg, then they separate around an island in the center and then go out to the Baltic Sea, out to the left of this particular map. And there are 7 bridges that that get you from one bit of the city to the other. And the challenge for the residents was, can you cross each of these 7 bridges once and once only? And however hard they tried, they just couldn't seem to. There always seemed to be one bridge that they hadn't crossed, and they weren't sure whether, have we tried all the possibilities? And it took Euler being asked about this problem and coming up with a clever shortcut to think about whether you can navigate a network like these bridges of Königsberg. And again, he used this trick of using a good diagram. So instead of all of these areas of land which somehow are irrelevant, he shrunk those to a point, and then the bridges, all that was important was how the bridges connected these areas of land. So the island in the middle has now become B, and so the challenge of doing these bridges was the challenge of, can you draw this diagram without taking your pen off the paper, so you run over each line just once and once only. And what Euler understood was, you don't need to try all the different possibilities. All you need to recognize is that if you do such a journey, then in the middle of the journey, if you come in on one line into a point, then you've got to go out on a new line. So most of the points have got to have an even number of lines coming out of them. There are only 2 places which possibly could have an odd number, which is the beginning of the journey when you set off on a line, and the end of the journey when you arrive. So there should be a maximum of 2 places with an odd number of lines coming out. But if you look at this diagram, then every point has an odd number of lines coming out of it. So it's impossible to draw this without taking your pen off the paper. Now, I was very excited, actually, when I was making a program with the BBC called The Story of Maths. So we had the chance, actually, to go to Königsberg and have a look at this, the bridges. Now, obviously, not all the bridges are there because Königsberg got very bombed during the Second World War. It was actually part of Russia, USSR. It's now actually called Kaliningrad. And it's still part of Russia, but it actually is a very interesting part of Russia because it's an exclave. It's surrounded by other countries, so you actually have to fly from Russia over other countries to get there. But we made this journey, and I was very intrigued to see, what bridges were left. Is it possible to do the bridges of Kaliningrad? And it's wonderful. It turns out that there are 7 bridges still, but in a different configuration. So some of the old bridges still exist, but there's a dual carriageway which has 2 bridges which run across the city. You can actually walk down. There are stairs to get you down into the island. So if you want to only do one of those bridges and then do another one, that's still possible. There's a railway bridge a bit further to the west of the city, which you actually can also walk across. And it turns out that if you draw the diagram for this new configuration, it's possible to do the 7 bridges of Kaliningrad. So I tried to persuade my film crew to do this wonderful journey. I mean, for me, visiting Kaliningrad was like sort of visiting mathematical Disneyland, but it's a very grim city, having been bombed heavily. So I think my film crew thought I was mad with the happiness I seem to have in visiting this city. There's actually 7 bridges isn't very many, so you could easily actually write them all out. But what if you had, say, like 50 bridges, and then then you don't want to have to try every possibility. It just takes you forever. Well, not forever, but quite a long time. And so actually there's an example of that, because the bridges around Bristol, and there are several kind of rivers that are crossing through Bristol. There are, in fact, I think it's maybe, I seem to remember it's about 45 bridges. And I discovered that there's an academic in Bristol who had actually analysed the graph that these 45 bridges make, and understood that it is possible to walk over all of the bridges once and once only. The bridges of Bristol is doable thanks to Euler's shortcut. then he wanted to actually do the journey. So no shortcut to that. It took him about 11 hours to cross all 45 bridges. But at least he knew Euler's shortcut told him that would be possible. So one of the first uses of maths for shortcuts for networks solved the bridges of Königsberg. But it's very interesting that networks themselves often have cunning shortcuts inside them. So people might have heard of this thing, the 6 degrees of separation. The rather extraordinary fact that our network of friendships means that it turns out that we can choose 2 people randomly across the world, and it seems like we can do a connection of friends to friends to friends to friends. With just 6 connections, we'll find a line of friends which joins one person to the other, and that's extraordinary. And it's the nature of a network which has this quality, which is called a small world network. So this is a network where there's kind of a lot of local connections. So we know a lot of people around our neighborhood, but then we know a few people across the world. I know, somebody in India, for example. And it's these few long-range connections which create a network which has this possibility to get from one place to the other in such a short number of steps. So this is very exciting, because sometimes if you want to create a network where there is those possibilities to get from one place to the other quickly, we know what we need to do. We need to create lots of local connections and a few global ones. And a lot of networks have this property, and one in particular is our brain. It seems like a neuron, if it wants to communicate with another neuron, takes advantage of the fact that the neurons are joined up in the brain rather similarly to those small world networks. This is actually a picture of Gauss's brain, and Gauss is actually a companion throughout the book as I sort of explore the range of different shortcuts that I've presented in the book. Because he seems to, he really is the master shortcutter. He seems to have a finger in every shortcut that I talked about: calculus shortcut, diagram shortcut, geometry shortcuts. So he's a companion throughout the book, and so I thought it was good to show his brain, which he donated to science afterwards. And scientists tried to understand, was there something special about Gauss's brain that meant that he was so good at shortcuts? And there is some research to show that his brain seemed to have more folds in it than a normal brain. So perhaps he was using some sort of fractal character of his folding of his brain in order to be able to make these fast connections and these shortcuts. Some other companions in the book are actually some other practitioners from different disciplines that I talk to. So each shortcut comes with a little pit stop between it, the shortcuts, where I go and talk to people from other professions, because I was intrigued. Do they have shortcuts that they use? Are they similar to the mathematical ones that I use? Or can I learn about new shortcuts that I could use in my mathematical world? Or are there things that there are no shortcuts? You just can't get around doing the hard slog. So, for example, I talked to Natalie Klein, a cellist, international cellist. I'm learning the cello at the moment, and I'd love some shortcuts to be able to play the pieces that I are hankering after playing. But she told me that essentially there aren't really any shortcuts beyond doing those 10,000 hours of practice that Gladwell talked about. And that's because actually that practice is physically changing the body. And it seemed like many of the professions I talked to where there aren't obvious shortcuts are because you're physically having to change the body, and that can take time. So an athlete, for example, needs to train. It's, drugs can do a certain amount. But that was the interesting thing about drugs for health. One of the things we thought it would take a lot longer to produce a vaccine, because generally it takes time to see what a vaccine impact on the body will be. So it's quite surprising we came up with a vaccine within a year. But it was very hard to shortcut it any further than that year. So Natalie Klein there, I talked to Susie Urbach, psychologist. Are there shortcuts to therapy? Well, there are and there aren't. Some conditions you can use CBT, cognitive behavioral therapy, amazing range of shortcuts, which kind of intervenes with the algorithm of how we think. But other times it takes a long time to rewire the brain. Again, something physical. Robert McFarlane is up there in the mountains. He loves walking. And I was intrigued. Does he like shortcuts? Because a walk is an interesting, you're enjoying the long way. That's like the praxis. You do a walk because you enjoy doing the walking. You don't want a shortcut then. But he told me a sort of intriguing shortcut he used to get off a mountain very quickly as the night was coming in. He was being benighted, a word I learnt whilst writing this book. And he created a mini avalanche to get off the mountain quickly. That was his shortcut. And the other guy there is Brent Hoberman, who's was set up lastminute.com. His shortcut to startups was flying very close to the law. So they're a range of people who join me on this journey. But the final shortcut is actually about the impossible shortcut, because it turns out there are some problems that we think there won't be a clever way to find the solution. And mathematics is kind of trying to identify the kind of mathematical problems where there are no shortcuts. And one of the famous ones you probably heard of, the traveling salesman problem. If I have, this is a bit like the network that Euler solved, but now we've got distances on the map, and you've got to find the shortest path to visit all of the locations once and once only. This is actually a map of Glastonbury. I do a gig at Glastonbury in the Astrolabe Theatre, and I often quite like to go and visit all the stages whilst I'm in Glastonbury. So I've been trying to solve the travelling salesman problem about the shortest way to get around all the stages. But we think there isn't a shortcut beyond trying all of the different possibilities. In fact, there's $1 million prize for anybody who can prove there are no shortcuts. This is a problem called NP versus P. So the power of mathematics is sometimes to show, well, don't spend your time trying to find the shortcut. There is no one. You just got to do the hard work. As I say, Gauss is my companion on this journey. And he summed up rather nicely this fact that the shortcuts that he came up with, that we have come up with as mathematicians, as I said, it's not about bunking off and not doing the work. It's actually getting you to a place where you can engage in the things you do want to do. So, he wrote towards the end of his life in a letter to a friend, "When I have clarified and exhausted a subject, then I turn away from it in order to go into the darkness again." So I hope some of these shortcuts and the shortcuts that are in the book that I hope you'll all been sort of excited to go out and buy will provide you with the shortcuts to get you to all of those problems that you'll enjoy spending your time tackling, rather than doing all the problems with the boring old hard work. Thank you.
Thank you so much for that, Max. It was really interesting. We're going to take a break now so that I can take some of that in. And while we do that, we've got quite a few questions have come in on Slido, but there's still room for plenty more. So do ask anything you want to know. And if you haven't got one, go there anyway and have a read through and vote up the ones you think are interesting so that we'll get to them. Otherwise, we're going to be back at 8:10. So I'll see you then. Goodbye. Okay, welcome back. It's now time for the Q&A, but before we get started, I just want to mention the Skeptic magazine is running its annual Occam Awards soon, and nominations are now open. There are two categories. One is the Occam Award itself, the award for a great act of skepticism or somebody who's been particularly good for the cause over the last year. The other one is the Rusty Razor, which is kind of the opposite. It's an award for somebody who has promoted pseudoscience or similar bad thinking, and it's usually a hotly contested field, so do get your nominations in. There are going to be links in the chat for how to do that. But otherwise, we're going to go straight to our Q&A, and our first question has come from Bremner, who asks, mental shortcuts are often terrible. He wants to know how you find a good shortcut and tell it from a bad one. And the example he gives of a bad shortcut is racism, making sweeping generalizations about whole groups of people. It's very efficient, but it's not great.
Yes, I think in some ways that's exactly what my book is trying to kind of highlight is, generally and it's sort of what Kahneman was talking about as well, the fast, intuitive heuristics. I mean, that heuristics is a sort of shortcut, but very often, as Kahneman has illustrated in his book, and I talk about as well, often don't get you to your destination. And I think sweeping generalizations is a sort of good example of that style of heuristic, because quite often what we do is to take sort of particular information, local information, just a small bit, and then extend it to the larger data set. So that's the wrong way to go. But it's interesting, why how do you judge whether a shortcut you come up with might look mathematical, but it might be actually faulty as well? So I think that's it is quite hard to judge in advance. So for example, how do you avoid the bias that might appear in a sampling, for example? There's the classic example of the polling in America early on in polls, when people were phoned up to ask their political opinion. Now, of course, it was at a time when only rich people could afford a phone, and so they got an incredibly biased sample, which wasn't representative. So, but my feeling is that mathematics, they are pretty robust, because often the power of mathematics, when we come up with a shortcut or a kind of argument, is that we have the power of proof to show why something has a particular measure of efficiency. So we have these measures of algorithms, for example, the polynomial time algorithm, a quadratic, a cubic. They will have different rates of getting you to the answer. So I think mathematics has got sort of inbuilt kind of ways to assess which ones are powerful, which ones are good, which ones will genuinely get you to the correct answer. So I think the more you can turn something into mathematics, the safer ground you're going to be on to know that your shortcut is working efficiently. But again, you have to be careful with this. I think the financial crisis can probably be traced to a financial model, a mathematical model, which people were using to shortcut navigating the economy. Now, if the financial system satisfied certain hypotheses, then you could prove that it was working. But the trouble was that suddenly the financial system went into a state where it wasn't satisfying those hypotheses, but we were still using the old model, which then everything just exploded and didn't do what the model was saying it should do. But that was a fault of applying the model that we thought, which was working in circumstances, but doesn't work in all of them. So, but I think I think the question absolutely highlights that there's a lot of shortcuts that we come up with. Mental shortcuts are of the quality of heuristics, and those, as Kahneman has so beautifully illustrated in his book, Thinking Fast and Slow, often just get you to the wrong conclusions.
Yeah, I think it's a deeply skeptical question as well, because a huge amount of what skeptics do and are interested in is alternative medicine is usually like a way to try to shortcut past real medicine. And if it worked, that would be lovely. But it's being able to tell which ones are good shortcuts and which aren't at all.
And I think you have to, that's why you have to test. So, you'll really know a shortcut's we might come up with a very radical new way of doing medicine that people are very skeptical about, to start with. But if we then go through the testing and the experiments and we come out, those skeptics are then converted. But that's the point. We need to do the testing in order to be able to. It's very interesting, because I think that there's an interesting kind of schizophrenic role that a scientist has to play, which involves being skeptical all the time, but also involves a sort of almost innocent kind of, maybe this madcap theory might work. And so I think the best scientists are those that can combine the rather kind of mad, try something really stupid looking with then turning on the skeptical side of their mind. And I often do that with my collaborations. I often find another mathematician who will play the skeptic role, and I might play the kind of just mad trying out silly ideas role, and then sometimes in some of my collaborations that kind of dynamic gets reversed. So yeah,
it's very difficult to come up with an idea and then not be too precious about it being proved wrong. It's so hard.
Yes, I mean that's what we fall into, that trap of just falling in love with our ideas and just not recognizing that now there's been enough evidence to show that I need to give up on this. But
we should move on. We're still technically on question 1 here. So let's ask Tom's questions. Tom wants to know: is the danger of shortcuts that they can be used by people who lack the knowledge of going the long way around and can be unable to detect or correct any errors?
Well, I think that's very interesting, because the best scenario is, of course, to understand the technique that you're applying. So you can know, for example, when actually this shortcut does not fit this model, and so it's not going to work in this particular case. And I think there is often one of the shortcuts is not to do the work to understand how the shortcut works, and then you find you're applying it in the wrong setting. So yeah, I think obviously the best case is to, but I think probably the best shortcuts are those where there's a kind of funny paradox that comes out in the book, which is that coming up with shortcuts often takes a long time and a lot of work. I think I saw on the slide, I had a little look during the break, somebody was asking, is there a shortcut to finding shortcuts? And I would say probably not, actually. But that's actually fine, because I think one of the fun things, I enjoy spending ages and then getting that aha moment of finding the shortcut. If it's been too quick, if there's too much of that's the proesis versus the praxis. I actually enjoy the hard work of coming up with the shortcuts, but the best shortcuts are those which can be implemented without necessarily having to know all of the technical background. I think calculus is a difficult one, because you really have to understand that to be able to implement it. But I think sometimes things like the data sampling, that's a good one, where you don't have to know the mathematics behind that to potentially implement that one.
I wonder if there might be a way of finding shortcuts to shortcuts, because I'm a software developer, and a lot of what I do is writing software that I would not be able to write if somebody else hadn't written the platform I'm doing it in, which runs on an operating system, which runs on a computer. All things could have been done longhand. I could type out the assembly code for the entire thing, start to finish, but I never would. It would never occur to me to do it. So
I think but you're exploiting other people's shortcuts. It's like, so somebody's dug a tunnel absolutely under a mountain, and then everyone else is going to go through that, and then they find themselves at the frontier again. And so, this is the whole point. My teacher at school said, okay, I'm going to condense 2,000 years of shortcuts into, the 5 years that we're going to spend learning maths at school. And I'm hoping my book is your shortcut to all the it's we're trying to compact everything down. So I think but coming up with the next, certainly you should exploit all the shortcuts that have been used up to that point, but then you hit your mountain and you've got to try and find out, am I going to get over to the valley on the other side? Then often that's tricky, knowing, finding that short. And actually, there's one of my favorite films is Good Will Hunting, with Matt Damon, who's the janitor who works in a maths department, and there are all of these problems up on the blackboards, and Matt Damon can do them in so quickly. He solves them, and the next day the mathematicians come in and they're like amazed. And what's always curious, I think intriguing, is that at the end of the film, Matt Damon doesn't choose to become a mathematician, and I think it's because he finds it too easy. So that it's not enjoyable. That sort of he isn't getting that praxis feeling of enjoying the work. I mean, what he finds hard work and he finds difficult to understand is his girlfriend. So he goes off and chases his girlfriend, and that's the kind of challenge for him. So I think actually sometimes the coming up with these shortcuts, sometimes the fun thing is that they do take time.
Yeah. But one of the questions coming up is from Igor, who asks, he often finds himself spending so much time coming up with the shortcut that it would have been quicker to just do the long way, do all the work. And is there a way to spot that behavior and stop it?
I so recognize that quality that I often find myself, thinking, well, actually, all this time I've tried to come up with some smart way to look at this. I could have actually just crunched the whole thing out. But in the long term, you're going to be remembered for, so spend the time once you've come up with that smart way of doing it. It might have taken you longer, but you're then going to be the shoulders on which the next generation will stand on, and they will be able to exploit that new way of looking at the problem that's you spent a long time coming up with. So I do kind of sympathize with Igor's kind of, because I've often found myself thinking, why don't I just crunch this out? Although actually, for me, I mean, the sort of mathematics I do very often, I can't avoid having to spend time doing the shortcut, but very often I'm trying to navigate kind of infinite structures, and unless there's no way to crunch through it all, I have to, if I'm trying to prove, for example, something about prime numbers, I can't do it kind of example by example because there are infinitely many. I have to find the kind of cunning way to look at all of them in one go. So often the sort of problems I'm faced with, I just cannot get away with crunching numbers, as it were, because there are just infinitely many of them.
Yeah, I found a number of times as well, I've tried to force myself to just go the long way, don't be clever, don't try to find a shortcut through, and then the next day I've had to do the same job again. And I've really wished that I'd put the time in.
Yeah, I mean, I think that's that's what mathematics is all about. It is understanding that, okay, you've got a new problem, but it's the same problem I did yesterday, but just with different parameters and things. And what I want to come up with is a method which it doesn't matter what the parameters of the problem are. This method will solve all of these, and that's mathematics time and again. The solution to a quadratic equation, doesn't matter what numbers are in there, we found a way that will solve all of them. So that's that kind of idea of infinitely many possibilities, but we find one way which will navigate those infinite spectrum of challenges.
Okay, so I'm going to move on to Dave's question. There's, I think, two questions that are more or less the same in the chat. They're both asking what your favourite shortcut is and what it's applied for. I'm going to ask Dave's version because it's the one most suited for a mathematician. What's the favourite shortcut you've ever learned, and is it useful for anything?
Well, I think that one of the most important shortcuts for me has been the idea of spotting a pattern in numbers. That's actually the first chapter is dedicated to the power of spotting patterns to a shortcut to understanding how a set of numbers is going to evolve. So, and in fact, in my own research, what I'm trying to do is to understand symmetry, and in particular, I'm trying to understand what sort of symmetrical objects exist out there, not just in 3 dimensions, but in higher dimensions. And it's a very wild problem. And the one way I've tried to simplify it is at least, can I count how many symmetrical objects there are with a particular number of symmetries? Say with 7 symmetries or 7 squared symmetries or 7 cubed symmetries. One of my big breakthroughs was to understand these numbers are not random, that there is a pattern to them. And actually it's quite similar to the Fibonacci numbers. So the Fibonacci numbers 1, 1, 2, 3, 5, 8, 13. Once you spot it, there's a pattern there because I add the 2 previous numbers to get the next one in the sequence. And then that allows you to start understanding that data set using that pattern. So for me, I'm very often looking for something like that. It's called a recursive function, but the dependence of the following things on the ones before, and what is the formula. So for me, when I was trying to understand this wild problem of these symmetrical objects, at least knowing there was some sort of connection to the way they built up, and there wasn't some whole new wild slew of things coming in, has been very powerful in my own research. And I think that's, looking for a pattern in data has been fundamental to the human species in its evolution, because that ability to spot patterns means that you can predict things into the future from the data that you've seen at the moment and be confident that that's where the data is going next.
Okay, Igor has asked, do you think people are predisposed to finding shortcuts, or is it a skill that we need to learn? And if you feel like recommending any particular book for that, then, obviously go ahead.
Yes, I think that, I think we are sort of all predisposed to finding shortcuts in a way, because they give us an evolutionary advantage. So I think that's why, going back to the pattern shortcut, I often say mathematics is the subject of looking for patterns. And when everyone says, oh, I don't have a mathematical mind, I say, well, I think the human species has evolved to be always looking for that kind of pattern, or the kind of fast, efficient way to do something, because that's going to give us an evolutionary advantage. So, sure, we're not all good at it. But I think that actually our species has got to where it is because it's developed these tools. Language, language is an amazing shortcut. We have one word which covers so many different examples of things. That's that's a bit like the diagram shortcut. You don't want to have a different word for every single type of chair there is. I mean, that's very powerful so I think we have evolved to be good at looking for shortcuts, but can you get better at it? Well, I think that's sort of why I think training as a mathematician does give you, even if you don't use your maths, that ability to think mathematically. And that's sort of what I try to illustrate in the book. Enough examples of things outside of the world of just mathematics, where thinking mathematically sort of gives you a way of approaching problems which, to avoid doing the long way. But there is a curious thing about, why are some people good at some things and not good at others? Actually relates to shortcuts, because I talked to a neuroscientist in one of my pit stop chapters, talking to other people, and I was saying, is there something about I'd already knew about the brain using this kind of small world properties to shortcut connections between the brain, but he discovered that actually he'd wanted to become a grandmaster at chess, and so he dedicated 10,000 hours to training. He'd gone to work with all of the great teachers in Russia, but he couldn't get kind of beyond master status. And he wondered, is there something about my brain which is stopping me being able to play at this very high level? So he turned to neuroscience and started analyzing his brain and grandmasters' brains. And it turns out actually grandmasters use a sort of shortcut, because they use less of their brain in order to be able to think about the problem. One of the troubles is when I play chess, I almost think too much. I analyze all the things very consciously, and it seems like he could show using an EEG that a grandmaster will be just using sort of two bits of their brain and sort of bypassing the bit where most of us do our cognitive conscious thinking. And so he kind of said, what we need to do is to find what is it that we are able to use our brains in this way. He said, he analyzed my brain when we were playing chess, and he said, you're not going to be a grandmaster because you're just, and he thinks it's something you can't train yourself to undo, but use this cognitive side. But he said, I bet you if we scanned you doing mathematics, you're probably doing that. You're probably not getting bogged down in all of the thinking, but you have an intuition, a very good intuition that, so it's interesting. He sort of illustrated that some tasks, our brains are very good at sort of using less of our brain in order to be able to quickly get to a solution.
I wonder if you can learn those intuitions to some extent, because when I started doing life drawing, one of the things I found was I had to stop looking at and oh, it's a leg, I'll draw a leg.
Yes.
Do that. You have to stop using that shortcut because your intuitions are bad. You have to look carefully, analytically think about the shapes and then draw them. But that was a few years ago now. And now I can look up and think, oh, that's a leg, and draw it because I now know what a leg looks like, which I did not then. You think you don't. So yeah, maybe these things are learnable, but something like chess, that's got to be.
His argument was that actually, there's a certain amount that you can learn, but he believed that actually this is, I think it's a bit controversial, but he was saying I can look at a child as that when they're first playing, analyze their brain and recognize that they might be able to get to master, but they won't be a grandmaster because they're already not thinking. I think he felt you couldn't unlearn this channel of thought process. And it's actually interesting because it relates to, I mentioned talking to Susie Orbach, the psychologist. I talked to Fiona Kennedy, who uses a lot of CBT and all of these incredible short techniques that we've developed to be able to change thought processes. But Susie Orbach deals with quite a lot of people where she describes it as I'm having to deal with patients where they've got to not learn a new language, they've got to unlearn a language. I mean, it's a bit like you having to learn whether not to see a leg. Here's hello. Now, the skeptics would love to see you. So here is Frederica, but she's a street cat, so she really doesn't like being picked up. But anyway, she managed to get her in. I'll give you treats afterwards if you stay around. Ugh. No, there you go. She's off.
It was more cat than we were expecting, so thank you.
Cool. Yeah, I've lost my ground. So, another question.
Yeah. So Paul asks, has the use of pocket calculators or now smartphone calculators diminished the incentive for finding shortcuts in mathematics?
Well, that's, actually, it's interesting because that's a whole chapter I've dedicated to sort of computational shortcuts. And in a way, a lot of the, mathematics right from the beginning has been about finding sort of a ways to avoid having to do long computations and things. That the shortcuts of even how we write numbers, if you think about it, are sort of starting to tap into more efficient ways to do things. So, of course, actually programming, as you know, as a software engineer, programming a calculator to do particular computations, do them quickly, it involves implementing a lot of these shortcuts. But I'm not too worried. A lot of people are like, oh, but they're not, is that a bad shortcut because you're not doing the kind of cognitive thinking but I'm actually pretty pro using a calculator as a shortcut because that's kind of like Gauss's, I would say, Gauss's strategy is saying, well, I don't have to, I'd rather spend my time doing some interesting thing with these numbers, and I will use the calculator as a tool to help me explore what's going on in these numbers rather than getting bogged down in the plodding of the actual computations. So I think used well, that a calculator can actually get you through the sort of things which are getting you bogged down so that you can't see the exciting part of mathematics. And I think there are some interesting sort of educational projects which are really trying to up that and use sort of not just a calculator, but real sort of good sort of mathematical programs to allow people to experiment and play in a way that you really couldn't do before. And after all, I sort of use software packages as a helpful sort of experimentation place to see what's going on. And if I didn't use those, I really would just not be able to get a feel quite often for the lay of the land. The thing is that they often only get you so far, that I can do some experiments and then I've got to leave it behind, because at the moment they're not good enough to come up with the proofs of why something is going on. But that's another interesting question. I mean, my previous book about artificial intelligence and creativity, one of the strands in there was, at what point will we get to code being good enough not only to just crunch through numbers and give us data, but actually come up with the reason why things are like that is. And I think there's actually some exciting news that will be coming up in the next week about progress on that. So keep look. It's embargoed at the moment, but look out for that coming up.
Okay. Gravy Earthling has asked, how do you distinguish between a shortcut that works 100% of the time and a shortcut that works 99% of the time, but brings the other 1%?
Yeah. Now that's a really good question, because some of these shortcuts we can prove that they're 100% effective. In a way, Gauss is one. Yeah, there's no question. But quite a lot of them are about that kind of slightly more dangerous area of, okay, yeah, well, there isn't but I something like traveling salesman problem. We know that there are algorithms that, for a certain percentage of networks will find you the most efficient solution, or, for example, will get you a solution on all networks which is within a particular percentage of the shortage value. And so, again, mathematics is very good at analyzing when something isn't 100%. And so then you can start to judge, am I prepared to deal with that sort of tolerance level? And so I think that's important. I don't mind having something which isn't 100% as long as I know what sort of region I'm in. So, again, that sampling thing, well, 1 out of 20 times you're going to get something which is way off. And that's really important, because, that's a kind of gold standard for a lot of experiments, that we have to get that sigma in that kind of range. But sometimes, well, if you do 20 experiments, if there are 20 research centers, one of them will do something and think it's significant, but 19 will have done the experiment and nothing interesting has come out of it. The 19 don't get reported because we're very bad at reporting things, negative results, and then the 1 out of 20 where something weird happened gets reported because that's exciting new revelation. And so that's why there's a whole new movement in science of reproducing experiments, because we need to make sure that has this crept in as the 5%, which which will get you published in a journal, but is this a bad 5%, as it were?
Yeah, there's a question further down the table from Dominic about the deal on our deal statement. I think they were just surprised that it's only 37% effective, and that feels like it's quite a small number.
Yes, yeah. No, you mean 30%. It's like 1 in 3, I think. Yeah, so you look at 37% of the data, but it's sort of a bit disappointing. You'd think, oh, surely I could do better than only 1 out of 3 times this is going to find me the most. But you've got to remember, how things could be laid out. First of all, there's a 1 in 3 chance that the best thing was already in the first 37%. So then, you're never going to win on that case. So we've already worked. So you think, well, maybe I could do 2/3. But then you've got to remember as well, you're going to be taking the thing which beats everything you've seen so far. So if the biggest prize is much later on, you're probably going to miss that big prize because you'll fall for something which is beating. So you can see that there are lots of ways that that actually you will fail to get the best thing. So again, you might say, well, how well does this strategy do in finding me at least something which is within a percentage of the best thing? So that's also another way. But it is it's kind of disappointing maybe that it's only 1 in 3 gets you the best thing. But I think that actually is still quite high, because I wouldn't expect actually this strategy to work very often to result in me getting the top prize in those boxes. So I actually think if you start to think about it, it is actually still quite high as a percentage to guarantee you getting the best of all in any of those boxes.
Yeah, and there are other strategies you can use to get, if you just need a certain amount of prize money or want to maximize the amount you might win. You just have to be very careful with these shortcuts, that you're using exactly the right shortcut for the job.
Well, I think, that's a very important message. There's a whole suite of shortcuts that I show the reader, and often the challenge will be, okay, well, which one of these is right for the particular problem that I'm trying to solve at the moment? So that is quite a skill, which weapon am I going to use? Sort of.
Okay, so Andrew from Peterborough asks, are we sure that light chooses the quickest path and bees choose efficient honeycombs? Could it be convenient coincidences and we're just ignoring a lot of examples that don't fit?
That's I think I think that that's a fair challenge, but so I think that's always one of the things in science is are you coming up retrospectively with a sort of argument to justify what you're seeing? But I think in the case of light, we sort of that would be very bizarre if it was coincidentally always finding that path, and we sort of have a rational. I mean, I think there's actually a very important point here, because science at the moment is being so wooed by big data that often we will find some sort of pattern going on or some connection between things, and we will almost be just happy with having identified that, and we won't actually question, is that why is that connection there? I mean, that's I think there's almost the power of big data is almost overwhelming, challenging. Well, is that just coincidence that something's happening like that, or is it the other part of the question is partly about sort of whether, for example, the honeybee sort of knows what it's doing, or is it how conscious is it in choosing? Because I use that word choose. So choose sounds like you got free will or something. So is the light got any other choice? Why is it choosing? So I think that's probably a bad choice of word, because it's sort of anthropomorphizing the thing, so it makes it sound like. But and saying nature chooses something. But I think that's the point is that the having a condition on a system which means that it tends towards a low energy solution is kind of the explanation for that choice, and it isn't a choice, it's actually determined by the system. So you have to understand why the honeybee comes up with that. I mean, again, I would say the honeybee finds that solution almost because even if you put a non-conscious or non-animal, if you just put a load of marbles in a wok, they will form that pattern. So that's almost what the bee is doing, is sort of the bees are collecting together, and it's not the bee itself, but actually just the physics of this thing which is doing the work for them. So you could say, yeah, my argument is wrong there, because it isn't the bee finding that because it uses the least amount of wax. It actually would happen even if wax was cheap, I suppose, actually. Yeah.
Yeah, I know. I heard about the light taking the fastest route phenomenon at A-level physics, I think. And then at university, they taught us that you can actually derive quite a lot of laws of nature from a single principle, which is minimizing action. There's a thing called action that they have defined for this purpose. But I just like that as a kind of, the laws of nature themselves are kind of just a shortcut to get to wherever you're going as fast as you can.
Yeah.
Very nice. Okay. Ed Edmondson has a question about the bridges of Königsberg. It says that you showed how having too many odd-numbered nodes prevents you from being able to get around everywhere, but is it the case that if if that condition isn't satisfied, you definitely can do it? And if so, how do you?
Yeah. Now that is very interesting because, it's not at first sight. You can see immediately why you can't do it if there's more than two which are odd number. But why? Is it still the case that if there are two, for example, you can do it? And that's something that Euler proved as well. And in a way, that's harder to prove and more striking. It's nice because it actually tells you the beginning and the end of the journey. You know where to start and finish. So I think, if I remember right, you either have to have two places with an odd number or none. So if there are none, you actually come back to the beginning from where you started. So and if there's one, I don't think you can do it because that will be a place where you start from there, but where do you finish? You have to finish again at an odd number. So
can you have just one with an odd number? There must be an even number of ends of lines altogether.
There you go. That's interesting. Yeah. So unless you're I suppose. Yeah. And that's a good point. So you there you go. You've already proved you can't do that one. But I think it's interesting to analyze, have a look at the proof. It's not too difficult for why. I mean, it's a sort of, if I remember, it's a sort of inductive proof because you sort of remove. I mean, one of the things Euler did as well with this kind of strategy is coming up with a sort of formula for the connections between number of vertices, edges, and faces of a polyhedron, and it's kind of similar sort of world where the way you prove that is to kind of remove edges and make the problem smaller. So if I remember, the way you prove that you can do a path is doing this kind of minimal reduction thing. So you go down to a smallest counterexample and then you show how to remove something, and you got down to something you can draw, and then you reinsert the edges that you removed. So you can show that if you can draw this thing, then you can draw the larger thing. So that's a kind of classic strategy of kind of take this minimal example where the thing fails and then show how to make it even smaller, and then the thing must work, and then you build back up to the thing which you said had failed and then make that work.
Yeah. Okay. Andrew's asked a question about the numbered blocks on the shelf behind you. We might have to put you full screen so that everybody can see this. Yeah, up there. I think that's the number 357. Is that?
Yes. So people can put in the chat any interesting properties of the number 357. I mean, for example, it's not prime because it's divisible by 3. But actually, these were used. The very first. The first TV I did actually was a game show called Mind Games, which I took over from Simon Singh. But then after we did that, the producer said, "Oh, I'd love to make a program about your first book, which is about prime numbers." And so we had a sequence quite early on where kids held. So if you look on the other side of that, it says 105. So this was illustrating how primes are the building blocks of numbers. So they turned the blocks over, and 105, and then they pulled apart, and it read it's 3 times 5 times 7. So, but they let me keep the blocks. The other ones, you can see a P up there maybe as well, which is on a octahedron. So we actually use these. One of the great discoveries Gauss made was that prime numbers seem to be get rarer and rarer, but the way they get rarer seems to be in a very uniform way, and it's almost like they're like 1 in 4 numbers up to 100 is prime, 1 in 6 numbers up to 1,000 is prime. So they seem to thin out, and Gauss discovered the pattern for how they thin out, and so they seem to be very random. So one of the models is that they're thrown by sort of prime numbered dice, and the number of sides on the dice gets more and more. So those were the dice. We got a dodecahedron with a P on it, and the cube, and the actually my producer on that program, he said, look, I think I'm about to be sacked by the BBC and I really want to go to Vegas, so can you find some spurious reason why we must go and film a sequence in Vegas? So I was like, okay, I think I've got one. We can go to the craps tables in Vegas and explain why Gauss came up with this kind of model of prime numbers as being thrown by dice. He said, yeah, that's perfect. So we went off to Vegas and filmed. That's in the olden days of making TV when you could go glamorous places.
We don't have a lot of dodecahedron dice in Vegas, do we? There's not.
No, very disappointing. So that's why we had to bring our own.
Yeah. Go to Vegas and bring your own dice. They love that. Okay.
A bit suspicious, exactly.
Yeah. We're going to go on to the last question now, but it's potentially quite a big one. Igor wants to know, do you think mathematics is solvable? Do you think at some point we'll discover all of the shortcuts there are?
That's very interesting, because in a way I'd say that relates to one of the great theorems of the 20th century, which is Gödel's incompleteness theorem, which actually is a proof that in a way maths can't be completely solved, that there is always something left over which can't be proved. So Gödel's incompleteness theorem says that within any system for mathematics, about numbers, for example, that there'll always be a true statement about numbers which can't be proved true within that system. So it's almost built into the whole of mathematics itself that we'll never be able to completely solve it. So, which I think is rather a beautiful use of mathematics to show its own limitations.
Yeah, and I think a lot of the statements in that category as well are ones that we probably, they're the sort of shortcuts we can use most of the time. Like mathematicians have checked from up to billions of digits. And it's like, we can probably...
You see, that's all right. You're talking like a physicist or an engineer,
yeah.
Because that for a mathematician, it just doesn't wash. And prime numbers are the perfect place. I mean, there are some amazing conjectures that were made about prime numbers, which were checked up to so far, and then we proved that no, they actually are false. But the first place where they'll be false, a computer or a check would never discover. I mean, sort of the scale of numbers that just even on astronomical levels are huge. So for a mathematician, we really do, and especially statements about numbers, you can't get away with that kind of cutting corners shortcut. Yeah. It's
all the applied people, and yeah, we can, but no, you have to be very careful when you're talking in general. So, okay, so thank you for that. That was really interesting. We're going to take a break next week. We're doing every 2 weeks now since things started to open up again. We're going to be back in 2 weeks with Professor Francesca Stavrokopoulou talking about a subject almost as fundamental and important as mathematics, which is the nature of God. But that is looking to be really interesting. I'm definitely going to tune in for that. In the meantime, we're going to head over to our virtual pub, the Lock-in's Razor. So if you're joining us, I'll see you there. Goodbye.